Okay, let's get started. Today we are going to complete the introduction of stochastic shocks to dynamic programming problems. Given the recursive structure of dynamic programming problems, these shocks must also be recursive. Uh, what do I have in mind? You remember the recursive structure of dynamic problems from the previous lectures. In the deterministic case, let's have an example, just a kind reminder. Uh, in the deterministic case, when we worked with policy functions, we related the current, we related next period's state to the current value of the state variable, and this was the point in in describing a policy function to describe next period state as a function of the current period state. By the use of the policy function, we can order longer chains of the state variable. So we can relate next period's state to current period state to previous period state, and the like. So this is the essence of recursivity. Given that dynamic programming problems have this basic recursive structure, uh, stochastic shocks must have the same recursive structure to fit into dynamic programming problems. So this is the reason why we need Markov processes. So today we are going to learn about the Markov processes that have the required recursive structure we need. Okay, um, to start to talk about Markov processes, it's instructive to have a simple example. Um, we have a Bellman equation, a functional equation. Um, it's very simple. We have a function of three variables, function f, where x stands for the current value of the state variable, endogenous state variable. So, okay, um, when we start working with stochastic models, we need to distinguish endogenous state variables and exogenous state variables. The endogenous state variables are the variables that are affected by the decisions of the agent, or agents. So endogenous state, for instance, in a firm model, the endogenous state is the capital stock, because the current value of the state variable, the endogenous state variable, affects the decision, and the decision is about determining next period's capital stock. So this is the endogenous state variable, because next period's capital stock, next period's uh, endogenous state variable will be the state next period on the basis of which the agent is going to make its decision. Y stands for the next period's value of the endogenous state variable, and Z is the exogenous state, the random shock in the current period. Um, in one way or another, this exogenous state variable affects the decision. For instance, it may affect the available options for the agent currently. In the second half of the equation, we use integration to calculate the expected value of the value function with respect to the probability measure lambda. You can see that z prime, next period's shock, exogenous state, affects the value of the decision the agent makes today, so the value of y, and this next period's exogenous state is unknown when the decision is made. So we need to calculate with its expected value. We know the distribution of the exogenous state. This is what the probability measure lambda describes. So in this functional equation, we calculate the expected value of the value function with respect to the distribution function, the probability measure of the exogenous state variable, the shock. In this case is not too interesting, because in this case, the exogenous shock is drawn from the same distribution time and again, and tomorrow's shock has nothing to do with today's shock. So there is no recursive structure. Shocks in the consecutive periods are completely independent of each other in this case. So we are going to work with this structure, but more interestingly, let's have the second equation, which looks really similar to the previous one, but there is a crucial difference. You can see that the integration is done with respect to another probability measure, a function q, which is called, this is another probability measure. This is called a transition function. A transition function describes the transition from today's shock to tomorrow's shock. So this is a similar probability measure, but in this case, the probability measure is dependent on the current shock. So depending on the value of the exogenous state this period, we will have different probability measure regarding the value, the distribution of the exogenous state next period. This is the basic ingredient of a Markov process, in which shocks are dependent on the past. In the basic case with which we are going to work the most, a chain of random shocks is dependent only the recent past, today's shock. So everything in the future path, the probability of any future path of the shock can be described as a function of the previous value of the exogenous shock. So this is the basic feature of a Markov process to describe the probabilities of paths of random shocks as a function of the shock itself. To this end, we will need a transition function. So we will define transition functions, and by using recursivity, we will learn how to describe the probabilities of certain path of shocks by the transition function, and then we will use these longer chains of shocks to calculate the expected value of functions by integration. And as a last step, we will learn how to define transition functions with the use of simpler functions like a policy function and a distribution function. So that's the agenda for the day. Let's go on with the formal definition of transition functions. The definition is simple. We have a measurable space. This is the state space for the shock, for the exogenous state, and we have a function over this measurable space. And to be a transition function, function q must have two key properties. According to the first, for a given z, for a given shock in the current period, q is a probability measure on the measurable space, and for a given set, which is a subset of the state space and an element in the related sigma algebra, q is a z measurable function. Later we will work extensively with transition functions, and you will see that time and again we will need to demonstrate that a given function is a transition function. It's formal. It's a formal work. We need to show that the function has these two key properties. More importantly, at this stage, let's interpret the transition function. You can see that q has two variables. The first variable is z, which stands for the current shock, the current value of the shock. And the second variable is a set, which is a subset of the state space of the shock, and it's an element of the related sigma algebra. So simply put, the transition function, as a probability measure, describes the probability that starting from the current value of the shock next period falls into the set A. So it's simply the probability of the shock next period falling into the set A, given that the current shock is Z. We can extend the probability, we can extend the transition function to describe longer dependencies. At the end of this lecture, I will show one instructive example. So I will show you a technique and a theorem. The technique is based on the theorem by which we can trace longer dependencies to first order dependence by the use of vector difference equations. Okay, so we will do this at the end of this lecture. Let's turn to more formal and technical results related to transition functions. We have two operators. The first operator is on z measurable functions. By the use of the first operator, we can calculate the expected value of f next period, given the current value of the shock z. And the second operator describes the probability of next period shock falling into the set A, given that the current value of the shock, the current value is drawn by the probability measure lambda. The first operator maps the space of non-negative z measurable functions into the same space. So by the use of the first operator, it is demonstrated in the book, we will have non-negative z measurable extended real valued functions. This theorem, which is theorem 8.1, is going to be used extensively in the later chapters, because this theorem ensures that by the use of the first operator, we will have functions that has the key properties which we require of value functions. The second operator creates probability measures. So by the use of the second operator, we can create further probability measures. So from the space of probability measures, the second operator creates a probability measure, so it maps from the space of probability measures into the space of probability measures. These two operators are related by theorem 8.3. For the first sight, it's not too interesting, but if we extend this equality, we will have a very seemingly strange result at the end of the slide. You can see that it seems to be strange, but the integral sign on the right is in the middle of the expression. It means that the probability measure, it's very simple. It seems to be strange, but it makes sense, because on the right, the integral describes the probability measure with respect to which we integrate, with respect to which we calculate the expected value of function f. I will show you in turn, I will show you the application of the theorem. Exercise 8.4 is built on the application of the theorem. So let's have a look at on this exercise. Okay, so we have exercise 8.4b, according to which we are supposed to show that the working of the operator can be decomposed. So this is what we need to prove. What's the meaning of this equation? So first of all, let's try to understand the thing we need to show. The operator in this form means the following. This is the expected value of the function f with respect to this measure, a probability measure. So we face another problem, which is good in a sense, because to interpret the operator over the period n plus m, we need to understand what this transition function means. So the first task to solve is to decompose the transition function qn plus m. So let's use the definitions. Let's start out from the definitions. So this is the transition function, and according to definition, it can be described in this way. This is an integral with respect to a very simple transition function. Okay, so this is true. Now we use that this is also a transition function, so it can be described as a double integral with respect. The first integral is with respect to this, the inner integral with respect to this measure, and the first integral is done with respect to this measure. So these parts of the two integrals are the same. Okay, so now we can apply the results of theorem 8.3 because this last equation is the same as the integral on page 218 of the textbook. So by applying the key result, we can write the following. And here comes the second integral. Please remember we just covered this issue in the lecture. So in this integral, the second integral describes the measure with respect to which we perform the integral. The second integral, I mean this one, the second integral is the definition on page 219 belongs to, falls under the definition on page 219. So applying the definition, we receive the following result. So we realized that we can use the definition to receive another probability measure with respect to which we can perform the integral. We can go on with this recursive decomposition, and if we make further steps, in the end we will receive that the transition function can be decomposed in this way. So now we are one step closer to the thing we want to demonstrate, because now we have a meaningful decomposition of the transition function. So now we can turn to the operator of the task, because okay, so we have this operator which is another again, this is an expected value performed or calculated in an integral done with respect to this probability measure we have just decomposed. So we can rewrite this expression by the results we just received, and having theorem 8.3 in the bag, now we are not scared that there is an integral sign in the middle of the expression. This is just normal. This is the reason why I wanted to show you this exercise, because to solve this exercise we need to rely heavily on theorem 8.3. According to theorem 8.3, we can move this integral sign to the front. So it's the same as writing that, okay, this n is terrible. we use the theorem and the definitions. The second integral, the inner integral, can be highlighted. So this is a distinct unit in this expression. And as a result, we will have the following. This is operator 1 from the textbook. So it's the same as this expression. This is a small n. Okay, so we let the operator work in the middle of the expression. So as a result, we have this part of the expression, and altogether it means that we integrate this function TMF function we integrate this function with respect to the probability measure Qn. Formally, it means the following. And this is what we were supposed to show. That's all. Now it's time for us to study the possibilities of using transition functions in describing the probabilities of longer chains of shocks. So simply put, we will use transition functions in describing the probabilities of longer chains of shocks. In the basic case, we have a probability function that describes the probability of next period shock falling into a set A given the current value of the shock. This is the transition between two consecutive periods. So the plan is to use this function to describe longer chains of transitions, not from this period shock to next period shock, but from next period shock to the following shock and the like. So to do so, we need some simple definitions. Later, we will use extensively the definition of finite or partial histories of shocks. ZT history consists of a T period history of shocks, and in the same vein we can define infinitely long chains of shocks. So what we are going to do is to describe the probability of a given shock chain, a chain of shocks, falling into a measurable rectangle. So we have a measurable space which is a t-dimension product space. So I say t-dimension because we are interested in describing the probabilities of shocks falling into a given measurable rectangle in t periods, where t describes the number of periods. You can see that the probability measure we can build, mu t, describes the probability of the chain of shocks falling into a given measurable rectangle. This measurable rectangle, this is a t-dimension product space, the element of a t-dimension product space. B is described by a chain of intervals. So this probability measure describes the probability that the shock in the first period falls into the interval A1, following that the shock in period 2 falls into the interval A2 and the like. Okay, so we can have, by the use of integrating the one period transition function, this is a chain of transition functions, and integrating all the t transition functions describing the transition between consecutive periods, we can build a probability measure that can describe the probability of a chain of shocks falling into a given measurable rectangle. We can use the same principle we used previously. So given that mu t, or our new probability measure, has the adding up property on disjoint rectangles, we can extend this probability measure to algebra E of finite unions of measurable rectangles. We use again theorem 7.13, and by the Carathéodory and Hahn extension theorems, given that this is a probability measure, so this is finite and this is z finite, we can extend this probability measure to the related sigma algebra of the product space, related to the product space. We can extend, so now this time we have a probability measure for a finite chain of shocks, but we can proceed to infinite histories of shocks in the same way. So we have the family of all finite measurable rectangles, and we have the algebra of all finite unions of all finite measurable rectangles, and the related sigma algebra, the smallest sigma algebra, which is generated by the algebra. We have the same measure, which has the adding up property. This is additive. So the measure has the adding up property, so it can be extended to the algebra, and from the algebra it can be extended to the sigma algebra. So we do the same thing, and now we have a measure, a probability measure, on the measurable space of infinite histories of shocks. Before turning to Markov processes, we need some elementary theory of stochastic processes. We don't need much. We only need some elementary concepts, just because Markov processes are going to be defined as a kind of stochastic processes. So to describe Markov processes, we need some definitions coming from the theory of stochastic processes. So first of all, let's define stochastic processes. A stochastic process is defined on a probability space that has three components. First, there is a sample space omega that contains all possible outcomes. There is an event space, which is a sigma algebra, and as such it is a family of subsets of the sample space. We will have some simple examples to shed some light on these concepts. And we have a probability function. This is the third component of the probability space, a probability function that assigns probabilities to each event in the event space. So these three components make up a probability space on which a stochastic process is defined. And on this basis, a stochastic process contains an increasing sequence of sigma algebras. This is an increasing sequence of families of subsets of the sample space. I will try to explain it to you in turn. We have a measurable space on which the outcomes live, and we have a sequence of functions. These functions are the random variables which can be ordered into simple path, and every single function, every single random variable must be measurable in terms of the related sigma algebra. Okay, these are very abstract concepts. So let me try to show some simple, very primitive examples to shed some light on the meaning of these concepts. So let's take as a first example the process of throwing a dice one time. In this case, omega, the sample space, has 6 elements: throwing 1, throwing 2, and throwing 3, 4, 5, 6. F, the related sigma algebra, is the family of all subsets. All, it's very important. It's the family of all subsets of omega, and the sigma algebra contains elements like throwing 1, or complex events like throwing odd. And the probability function assigns probabilities to each event in the event space. For instance, throwing 1 has the probability of 1/6, and the probability of the event of throwing odd has the probability of 0.5. We can describe more complex processes with these concepts. So if we have the experiment in the example, if we have the experiment of throwing a dice 3 times, then the sequence 1, 6, 4 is a sample path, and the event throwing the sequence 1, 6, 4 is an event in the sample space, and we have the probability. And this path 1, 6, 4 is also in the sigma algebra, so this is an event, and the probability function assigns a probability to this event. So I guess the most difficult part of the above definition is the fact that the stochastic process defines an increasing sequence of sigma algebra. So I think it's that part of the definition that needs some explanation. So how to describe the related sigma algebras? You can see that example A 8.7 is a related problem in the workbook, and I strongly recommend you to solve this problem. It's about tossing a coin. So instead of tossing a coin, let's stick to throwing a dice. So first of all, we need to create a set of all possible sample paths. This is AT. So you can see that this family, this set, consists of all the possible outcomes, chains of events, chains of outcomes, throwing 1, 3, 5, 6, for instance, if the experiment is throwing a dice 4 times. So if t, the time horizon, consists of 2 periods, then A2 consists of sequences like 1, 2, or 5, 4, where the sequences are ordered. So throwing 1 and 2 is not the same as throwing 2 and 1. So we have a set, once again, we have a set of all possible sample paths, and we create the smallest possible sigma algebras that contains all these families. So we will have F2, the smallest sigma algebra containing A1 and A2. That's all. So in this sense, the sequence of sigma algebras is increasing because, for instance, F3, the sigma algebra related to the 3-period problem, contains the sigma algebras related to the 2-period problem, because you can see in the definition of Ft that this is the sigma algebra containing all the previous all the families of subsets related to the previous steps. So on this basis you can solve, and I strongly recommend you to solve example 8.7, which is about tossing a coin, and you can see how to use the same definitions in describing different but similar problems. There is one more thing to clarify very briefly: the measurability of the function sigma t. Here we can use what we know about the measurability of functions. So a function is measurable if the event when the function is greater than or equal to a real number is in the sigma algebra. To have two very simple examples: to throw a number greater than or equal to 10 in t in the second period is impossible, but f being a sigma algebra contains this event, the empty set. Or as a second example, to throw a number greater than or equal to 3 in the second period is possible, and events like throwing 1 and 5 or 5, 3, 4, 2 are in the sigma algebra, so the function is measurable again. So simply put, to ensure measurability, all we need to do is to properly construct the sigma algebra. So if we have a proper sigma algebra, our random variables will be measurable. What we need to keep in mind is the fact that sigma algebras related to any given t, to any given period, so these sigma algebras contain all the families of subsets of omega related to the previous problems. Okay, and on this basis, we are in the position to define Markov processes. A first-order Markov process is a stochastic process with the very important property that the probability that the random variable stays in a given measurable rectangle. So in other words, the probability that the shock in the consecutive periods random variables stay in given intervals, this probability depends only on the recent past. So instead of explaining this probability with a long chain of the random variable, the most recent, for instance today's shock, is sufficient for us to describe the probability of a given path of the random variable. We have two definitions which sound similar, but they are different. The first is stationarity of a Markov process. So a Markov process is stationary if the probability of a given path of the random variable is independent of the time. So no matter when we start to study the probability of the chain of shocks staying in a series of given intervals, these probabilities are all the same irrespective of t. So if we have such a Markov process, it is said to be stationary. Another concept is Markov processes with stationary transitions, in which the probability that the shock next period is going to fall, the shock next period falls into a given set, a given subset of the state space, this probability is independent of the past. So we can describe, by the use of a transition function, we can describe the probability that the shock next period falls into a given set, and this probability, if a Markov process has stationary transitions, this probability is independent of how we got into today's shock. So the past doesn't matter. Note, please, and think about it, that these two concepts are not the same. So a Markov process can be stationary while not having stationary transitions, and the opposite is also true. So in the first case, a Markov process can have time-independent probabilities, why the probabilities depend on the past. They depend on the past, and the opposite. A Markov process can have time-dependent but past-independent probabilities. So once again, stationary Markov processes and Markov processes with stationary transitions are not the same. Now that we have probability measures interpreted on longer periods, longer chains of stochastic shocks, by which we can describe the probabilities of stochastic shocks, chains of stochastic shocks falling into series of intervals. Now we can try to calculate the expected values of functions by integrating with respect to these probability measures. You can see in the slide that the ultimate goal is to trace back these integrals done with respect to these probability measures mu t to transition functions, but to do so we need some further definitions, especially the definition of a stochastic kernel, which stochastic kernel is really similar to transition functions, with one exception. A stochastic kernel is defined on or between two measurable spaces. In other respects, a stochastic kernel looks really similar to a transition function. So for a given value of the first variable, it's a probability measure, and for a given set in the second variable, it's a measurable function. So it has the same properties as a transition function, but it's defined between two measurable spaces. Of course, a transition function is a stochastic kernel where the two measurable spaces are the same, but a stochastic kernel is more general a concept because it releases the limitation that the two measurable spaces must be the same. On this ground, we can define further stochastic kernels. So if we have three measurable spaces and two stochastic kernels between the three measurable spaces, so P1 is a stochastic kernel between W and X, and P2 is a stochastic kernel between X and Y, we can calculate, we can define a third stochastic kernel P3 by integrating P2 with respect to P1 over A. If you give yourself a second to interpreting this integral, you can see that this is a two-stage process. So starting from W, this P3 as a stochastic kernel describes the probability that starting in W, we go in the next period to a set A. So this is the probability of a random variable falling into set A in the first period and falling into set B in the second period. So this is the reason why the new probability measure, the new stochastic kernel, in the second variable, it has a product space, a measurable rectangle. So it's the probability that starting from W, the stochastic process goes through A in the first period and B in the second period. You can see some important results. So if F, I omitted theorem 8.7. According to theorem 8.7, the function f must be integrable with respect to P3. But if function f is integrable with respect to P3, then this integral can be decomposed into two integrals. The first integral is done with respect to P1 and the second is done with respect to P2. And the most important result is in the end of the slide. At the end of the slide, you can see that the initial integral, where the expected value of the function is calculated with respect to mu t, a t period probability measure, can be traced back to a chain of integrals with respect to the transition functions. This is a very useful and important result. And in this term, exercise 8.8 and 8.9 are very instructive, so let's have a look at them in turn. This is exercise 8.8 B, so we will focus on part B of the problem. In part A, the only thing we need to do is to show that mu t is a stochastic kernel. To do so, we need to base our argument on the definition of stochastic kernels. So we need to examine whether the function ut has the properties of stochastic kernels, and it does. In part B, which we are focusing on now, we want to show that, actually, let me change the order. that mu t as a stochastic kernel can be described as direct products of two functions in two different ways. So we need to show that these two direct products of stochastic kernels are the same. Okay, so we need to show two things, and this is what we are going to do. So let me describe what it means. This can be described as an integral, and it describes the probability that the random variable stays in a given measurable rectangle through time, starting from z0, it stays in a given measurable rectangle, and we have another stochastic kernel given as a transition function describing the probability that the random variable starting from the value in period t minus 1 goes into the set A in period t. Okay, so according to theorem 8.5, we can write the following. So we follow the theorem and the definition in describing the direct product of these two stochastic kernels. So this is the function we integrate, and here comes the measure with respect to which we perform the integration. This is a chain of transition functions. Okay, we should realize that this part of the integral can be described this way. So the whole expression, especially this part of the expression, can be rewritten so instead of so we are describing this part of the expression as an integral over the set AT. So the whole expression can be turned into a chain of integrals of transition functions. And by definition, this is mu t, showing the probability that the random variable goes through the measurable rectangle B times AT. So this is a composite measurable rectangle. Okay. The measurable rectangle B describes the first t minus 1 sections of the measurable rectangle, and at describes the period t part of the measurable rectangle. And in the opposite direction, we are supposed to do, because please remember, we are proving two things. This is what we have done now, and this is what we are going to do in the second part of the demonstration. So here the stochastic kernel describes the second part of the process, starting in period 2 and lasting until period t. And the transition function as a stochastic kernel, starting from z0, it describes the probability that the stochastic variable falls into the set A1 in period 1. And the direct product the first part describes the probability that the random variable, after starting in Z1, stays in the measurable rectangle B. This is another B. And by definition, it is. So actually, this stochastic kernel and this stochastic kernel are the same, even if we can see different measurable rectangles in the place of the second variable. But these two measurable rectangles are the same. In the first case, B describes the first t minus 1 dimension of the process, and at describes the last period t dimension. And in the second example, in the second case, A1 describes the first dimension, and B describes the consecutive t minus 1 periods, the measurable rectangle belonging to the following t minus 1 periods. So that's the demonstration. The next exercise is exercise 8.9, which is pretty long and complex. So here we will only focus on the main results. In part A, we are supposed to demonstrate that a probability measure lambda can be defined as the product of two probability measures defined on two distinct measurable spaces, and it can be demonstrated that the function lambda is a probability measure. What you can see here, I'm pretty sure that it's quite familiar to all of you, because the function on the left can be interpreted as a joint distribution function, which is the product of two marginal distribution functions. So even if the demonstration, the proof is quite technical, the result is quite straightforward and often used. In part B, of the problem, we use this probability measure which we have just defined in part A, and we should show that the expected value of this function, which is gained by integrating the function with respect to this probability measure, can be written in two ways. So actually we can decompose the integration by parts of the probability measure. So we can do this in two ways, and our task is to show that this integration can be done in two ways. It can be shown, it can be demonstrated. We are not going to do this because, again, the proof is very long and technical. So here, let me mention the main steps through which we can complete the proof. You can see that when decomposing the integral, we will have two inner integrals. So first of all, we need to show that this integral is x measurable, hence integrable, and in the same vein we should also show that this integration leads to y measurable, hence integrable functions. We do this with different function types approaching a very general function f, and we need to show that measurability holds on the whole sigma algebra. Here we have an analogy. When it comes to extending probability measures to sigma algebras, in other words, when it comes to demonstrating that a probability measure, a function is a probability measure over a whole sigma algebra, even if the function was defined on a narrower family of sets, there we can use theorem 7.13 and the Carathéodory and Hahn extension theorems to show that the function is a probability measure over the whole sigma algebra. In the case of measurability, we don't have such theorems, so here we need to show formally that measurability holds over the whole sigma algebra, and we can do this by calling into play the famous and often used monotone class lemma. We didn't cover monotone class lemma in the lectures, but you can find it in the textbook. The bottom line is that we define an increasing sequence of sets over which measurability holds, and we show that over the union of these sets, measurability also holds. So we can show that the sets over which measurability holds form a monotone class. If you have a look at the monotone class lemma, you can see that proving that a family of sets is a monotone class, sometimes it's easier than showing or demonstrating that this family of sets is a sigma algebra. And we use the same monotone class lemma to show that the integral holds over the whole sigma algebra. So we form a family of subsets over which integrability. Sorry, not the integral. This integral holds. So we form a family of sets, an increasing sequence of sets over which this equality, system of equality, holds, and we show that this equality holds also holds over the union of these sets. So the sets over which the equality holds is a monotone class, so equality holds over the whole sigma algebra. That's the skeleton of the proof in the exercise. In this final part of this lecture, let's understand how to define transition functions on the basis of stochastic difference equations. Before doing so, let's understand the problem. In deterministic dynamic programming, we used difference equations very extensively. For instance, and most importantly, the policy function was a difference equation. Such a policy function in the deterministic case relates state next period to state current period. Okay, just a kind reminder, in the deterministic case, we don't have to make the distinction between exogenous and endogenous state. We have the state variable or state variables. Okay, so in the deterministic case, this policy function describes next period state as a function of current state. But when we move to stochastic dynamic programming, the random shock also has a role. It means that the policy function in the simplest case, the stochastic function has two variables, has two inputs. The policy function has two inputs. One is the endogenous state, and the other is the exogenous state. So, depending on the value of the exogenous state variable, the shock, the policy function gives different values to the endogenous state next period for the same endogenous state this period. So this is the way how the stochastic shock affects the decision that the agent makes. Depending on the shock, the current shock, the agent makes different decisions even if the endogenous state is the same. So simply put, even if we have a distinct value for the endogenous state this period, next period's endogenous state will be different depending on the different values of the exogenous state. So once again, this is the way how I am overcomplicating, I know. So this is the way how the exogenous shock affects the decisions the agent makes in terms of the endogenous state next period. Okay, so these are the basics. The main result here is theorem 8.9. We have a probability space on which the random shock lives. This probability space belongs to the exogenous state variable, and we have a measure space that belongs to the endogenous state variable, and we have the policy function. So my previous attempt will make sense, because at this point you can see the policy function, the stochastic version of the policy function, that has two inputs, two variables. One variable comes from the endogenous state, so the endogenous state is one variable, and the exogenous state variable is the other variable, and the policy function, the stochastic policy function, combines these two variables into the endogenous state next period. So we have the stochastic policy function, which is a two-variable function. One variable is the endogenous state this period, and the other is the exogenous state this period. And the policy function describes next period's endogenous state as a function of these two variables. This is a measurable function, and we define the correspondence as the inverse of the policy function. For any given set A, this correspondence, this inverse function, gives ZW points. We will examine it in turn, in detail. So, and according to theorem 8.9, on this basis, we can define a probability measure, a transition function that describes the probability that starting from the endogenous state Z this period, the endogenous state next period is going to fall into the set A. So let's try to interpret what we have. Let's try to dig deeper in what we have. We have a set A in the sigma algebra of the endogenous, belonging to the endogenous state variable. The correspondence gamma gives ZW points, such points to which the policy function gives endogenous state next period falling into the set A. Okay, so in this regard, this is the inverse function, no surprise. These ZW points make up a set in the ZW plane. This is a measurable rectangle. For any given Z, let's go on. For any given Z, we have a set of the shocks described by the Z section of gamma A. This is a set in W. Please refer to the definitions on page 198 of the book, of the textbook. And the question on this ground, the question of the transition function is the probability that from a given zt, so from a given value of the endogenous state in period t, we get to any endogenous state next period falling into the set A. No surprise. We want to describe this probability, and we can do this in two steps. First, with the given endogenous state this period, getting into A, set A, depends on the random shock. For a given zt, the inverse function gives a set of the random shocks, and all these random shocks ensure that the endogenous state next period falls into the set A. So we have a set of random shocks. This is important. We have a set to any given endogenous state this period, zt. We have a set of random shocks, wt, that ensures that the endogenous state next period falls into the set A. Second, in the second step, we need the probability of getting from zt into zt plus 1 next period. So we need the probability that the endogenous state next period falls into the set A. And this probability is described by the probability measure, uh, which we can use to define the transition function. That's all. Theorem 8.9 shows that the transition function we have just defined has the required characteristics. So let me summarize this argument before moving on. We want to describe the probability that the endogenous state next period falls into a set A given zt. This probability for any given zt, this probability depends on two things. First, on the set of the shocks wt that ensure that the endogenous state next period falls into set A, and the probability that such an exogenous state occurs this period. So this is the reason why we need the probability measure related to the exogenous state. And I'd like to close this lecture by an example in which I want to show you how to trace higher order Markov processes to first order Markov processes by extending the state space. So actually there is let me have a look at the textbook. This is exercise 8.11 that shows that higher order Markov processes can be described as first order Markov processes if we properly adjust the state space. So let me try to show you what it means. So let's have a quick exercise at the end of this lecture. We have a measurable space and a function that describes that the variable falls into a given set, assuming that the variable fell into a pair of interval sets in the two previous periods. It is a second order process because we describe this probability in terms of the values of the two previous periods, and according to the exercise we can describe the probabilities of such a second order process as probabilities of a first order process, assuming that we adjust the state space properly. What do I mean? So normally in the first order process, a transition function describes the probability that we get from a point in a one-dimension space on the real line. So the probability that we get from a point on the real line into a set on the real line in the next period. We don't need to insist on such a structure because we can adjust the state space into a two-dimension space in which the point from which we start has two dimensions, which has the point has a timely interpretation. So one coordinate of the point belongs to period t, the other coordinate belongs to t minus 1. So the transition function does the same. It describes the probability that starting from a point we get into a set. But this point is not supposed to be a one-dimension point. It can be a two-dimension point with the coordinates having time interpretation. So in this case, we can use a similar transition function in which the point from which we start has two dimensions. I want to show you an example which we the structure of this example we will use extensively later. So I defined a very simple second order process with a random variable, and you can see we can describe the dynamics of the second order process with the first order matrix difference equation. And so this is an idea we will use later very extensively. Okay, so this was the day's lecture, and see you soon.